Dear colleagues, let me check the sound. Okay. Yeah. We warmly welcome you to our first 2019 already webinar, which is called ScanT, a shortcut to reliable AFM results. And let me introduce our today's lecturer. This is my colleague, the head of the director of R&D department in NT-MDT spectrum instruments, Dr. Vyacheslav Polyakov. And today he will give you the lecture. And if you get any questions during the lecture, you're welcome to write them directly to us, and we'll try to answer to all of them in the end of the webinar. So, Vyacheslav, you can start.
Thank you, Stanislav, for introduction, and I would like to very warm welcome all attendees of our today's webinar that is called ScanT, a shortcut to reliable AFM results. The agenda of our today's talk is the following. After a brief introduction, we'll describe our motivation for the developments of two new techniques that we call ScanT and rapid scan technology. Then we will move to the main part of today's talk that refers to automated optimization of scanning parameters in tape-in mode AFM. We will consider the physical background, basics of algorithms, and examples of applications of recently developed ScanT technology. Then we will go to rapid scanning and introduce the rapid scan technology, and we'll make some conclusions about today's presentation. So let's get started with a brief introduction. Well, atomic force microscope was proposed more than 30 years ago. It was in 1985 when Binet, White, and Gerber introduced the first instrument, and since this time the atomic force microscopy was widely developed. And at the moment there are a lot of AFM methods available, and a lot of instruments are commercially available, and there is a number of companies that supply the commercially available high-quality AFM instruments. So the technology was widely spread because, first of all, it allows the 3D imaging of surface topography with very high spatial resolution. But at the same time, along with the topography measurements, AFM allows to image nanomechanical, electrical, magnetical, and other surface properties with a nanometer scale spatial resolution. In marketing purposes, we usually say that we have more than 50 AFM modes, and every day new and new AFM modes appears in the community for new and new applications to measure the samples that was not measured before, or to measure some kind of properties of the sample that has never been measured before. AFM is a good tool because it can be combined also with the optical techniques in a wide spectral range, in ultraviolet, visible, infrared, or even terahertz ranges. And there are a number of AFM Raman, nano-infrared AFM, infrared and terahertz scanning near-field optical microscopes. Atomic force microscopy can be used under different environments. For example, in vacuum, liquid, or controlled atmosphere, it allows to vary the sample temperature during the experiments. In general, there are a lot of atomic force microscopes available, but average microscope would say have a field of view of the order of 100 microns in X and Y, and 10 to 20 microns in Z. And the typical scan rates in atomic force microscope is 1 to 2 lines per second. So since the development, since its introduction, AFM is widely spread, and at the moment there are a lot of commercially available instruments in the market, and one of the well-known companies is our company, NT-MDT Spectrum Instruments, and we have the whole range of both AFM and combined AFM Raman systems, starting from relatively simple educational to science level instruments, and up to the completely automated systems like Vega AFM that is that realizes the whole set of available complex and modern AFM modes on the large samples of up to 200 millimeters in diameter. There are a lot of AFM modes, but basically the whole set of AFM modes can be spread into three large groups. The first group is a contact AFM that historically appeared the first in the market in the instrument, where the sensitive part of the atomic force microscope cantilever is constantly in constant with the sample. Another large group of the methods is so-called resonant oscillatory atomic force microscopy, called as well as a tapping mode AFM or AFM, or semi-contact AFM. That is the mode where the cantilever oscillates on its or near its resonant frequency, and the feedback system supports the value of the amplitude of the cantilever oscillations by moving up and down the sample, and this signal is then recognized as a topography of the sample. And the third group of methods refers to non-resonant oscillatory AFM, where either the sample or the chip of the cantilever oscillates with a frequency that is much lower than its resonance. So all these three groups of methods are available. These all three groups of methods are base for the further development of different AFM techniques. And despite the AFM is quite good imaging, it has a scan rates of about 1 to 2 lines per second, and at the same time it has a lot of AFM modes and allows to image many properties. But despite all these strong points, AFM is relatively slow and quite complex instrument to operate. And this is one of the first motivations for us to develop the specialized technology that allows to operate with the atomic force microscope in the more easy way and in the faster way. Another important point that within the whole set of AFM modes, more than 90% of publications where AFM is used are made using the most common tapping mode AFM. And according to our own statistics, about 10 to 15 publications, even in the referred journals, in the AFM images that are published in these journals, in these articles, there are some artifacts that refers to the wrong adjustment of the scanning parameters in tapping mode. Taking into account that the industry is moving forward and we are constantly developing new devices like Vega AFM, that is completely automated system to measure the large samples of with a diameter of up to 200 millimeters, or developing the systems that are integrating atomic force microscopy with optical methods in the infrared range, and in fact allows to make the infrared spectroscopy with the spatial resolution of 10 to 20 nanometers. It becomes extremely important for further development to automate as much as possible the adjustment of parameters, of scanning parameters in one of the basic modes of AFM, in the tapping mode. And now we are moving to the main part of my today's talk, the automated optimization of scanning parameters in tapping mode AFM, and we will consider the physical background, some basic algorithms that we propose, and a numerous example of application. So let me first of all remind the basic principle of the tapping mode, that is the most common and the most frequently used AFM mode. In tapping mode, the cantilever, the sensitive element of atomic force microscope, oscillates on or near its resonant frequency, and when the cantilever approaches the surface of the sample, the amplitude of cantilever oscillations decreases. We then select some set point that is lower than the amplitude of the three cantilever oscillations. And during the scanning, the feedback system moves the sample up and down, keeping the amplitude of the cantilever oscillations equal to set point, and this signal is then recognized as a sample topography. So, while operating in tapping mode, there are four key scanning parameters that the AFM user have to adjust to get the proper image. First is the amplitude of cantilever oscillations. The second one is a set point amplitude that feedback system will keep constant. The third one is the integral feedback gain and the scan speed. All these four parameters drastically influence the quality of the AFM results. There are also two additional scanning parameters: the low pass filter band and proportional feedback gain. And the AFM customer has to adjust all these 4 or even 6 parameters at the same time. Like a multi-handed person, to get the proper image. Knowing some known parameters. The parameters of the probe are known. We know the resonance frequency and Q factor of the probe, and maybe some other parameters of the probe. Now, of course, we have the conversion of the magnitude signal to the real amplitude of cantilever oscillation that can be measured, and we have some knowledge about the sample. We often know the sample roughness or sample stiffness or some other parameters that we approximately know before the experiment. So the question is it possible to automatically optimize all these scanning parameters while operating in taping mode to measure the topography and phase contrast of the sample? For example, is it possible to develop some system that would allow to measure some samples, including gentle samples like fluoroalkanes F14, H20, that is given in this video example? That is quite difficult sample to measure because when we measure the sample with a low force, well, we have some artifacts that refers to the parachuting effect. If one would try to increase the force acting between the sample and the cantilever, the sample is damaged. The sample is crashed in this example. And is it possible to develop some system that would allow, by pressing literally one button, adjust the key scanning parameters like set point, feedback gain, and others like scan speed, that after some adjustment, it would become possible to get the high quality and reliable image, like in this example, and even to see that some particles on this sample were dispersed by the high force. Well, this is the example of the scan image of this kind of sample, and it looks like it is possible, but before we will develop this technology, we have to take into account some basic physical principles of taping mode. We have to, in general, recognize how the feedback system works in taping mode AFM. And this is important. This is important because the adjustment of the feedback system has very straightforward and very important influence to the results. We have to consider the parachuting effects, so-called parachuting effects, and the effect of mode switching in taping mode AFM. And we have to think how to optimize actually the at least integral feedback gain for taping mode AFM. And in general, as in any optimization problem, we have to recognize what should be objective function for this kind of optimization. And within the next several slides, I will try to briefly cover the very basic physical principles of all these steps that are essential to get some algorithms that allow to automatically adjust the scanning parameters in taping mode. So how the feedback system works in taping mode and how the parachuting effect, so-called parachuting effect, would influence to the AFM results. The development of the amplitude of the cantilever oscillations on the distance between the cantilever and the sample theoretically has the way that is shown in the down left part of this slide. When we are far away from the sample, the amplitude or the amplitude signal that we call the mag signal is equal to Mach 0 that corresponds to the amplitude of the free cantilever oscillations. When the cantilever starts to interact with the sample, the amplitude almost linearly decreases down to zero. And during the scanning process, in taping mode, we set up the set point that is equal to usually that is somewhere between the half of the Mach 0 signal, half of the free cantilever amplitude oscillation, and the free cantilever and the free amplitude of cantilever oscillations. And then the feedback system keeps the Mach signal constant equal to set point by moving sample up and down. Feedback system works with the error signal. The error signal is equal to the difference between the between the Mach signal, the current Mach signal, and the set point. Let's consider what would have if we are trying to scan the simple step, like a step of the calibration grating. The error signal, that is an input signal for the feedback system, will be equal to 0 before we will come to this step. Once we come to the step, the amplitude of cantilever oscillations almost immediately becomes equal to 0. This means that the error signal becomes equal to actually set point. Well, then when we are on the step, the error signal becomes equal to 0, and then when we jump out of the step, the amplitude of cantilever oscillation becomes equal to the Mach 0, that is the amplitude of the three cantilever oscillations. And as a result, and this is just the basics of how integral feedback system works, and as a result, we have the profile that looks approximately like this. We have the linear dependence on the beginning and in the end of the sample with the different inclinations. The inclination of the part that corresponds to the situation where we jump from the step to the where we jump from the step is lower, and this effect calls parachuting. So the parachuting is the behavior of the cantilever and behavior of the scanner and the corresponding artifacts that appears because that appears in time when the cantilever does not interact with the sample. Before the feedback system will move the cantilever back to contact, back in interaction with the sample. In practice, these artifacts look like this, look like stretches in both topography images, less on the top part of this slide, when we move from left to right in forward direction with the cantilever, or when we scan in the backward direction from right to left. And quite the same artifacts appears on the phase imaging that looks like shadow. Well, first of all, it is worth to mention here that these artifacts can be minimized by using a simple arithmetics, because anyway, scanning each line of the scan, we have the forward and backward signal. Why not to use it? And if we know some quite simple arithmetics, we can subtract this phenomenon and decrease the influence of the parachuting. For example, as shown in this slide, when just the simple arithmetical transformation between them. Simple arithmetical transformation from the forward and backward data gives us the better result. By the way, it is also quite useful when operating with the phase imaging, because if we suppose that we have the sample with some kind of topography feature and at the same time with some kind of, let's say, material contrast, where the phase contrast corresponds to the dissipation of energy that happens between the cantilever and the sample, and if we have some kind of material feature here, we will have in the phase contrast two areas. The stray contrast that corresponds to the topography of the sample, and another area that corresponds to the material contrast where we are interested in. So the useful signal. And this kind of signals, taking into account the parachuting, can also be minimized by applying these simple arithmetical procedures. And this is one of examples of some kind of surface, of polymer surface with the object. We have the height, the topography signals in the top row, and in the bottom row we have the phase signal that is corresponds to the forward and backward scanning direction, and the result phase contrast that is transformed arithmetically from these two slides has much more correct and much interesting contrast. So these features, like a parachuting effect, should be taken into account while adjusting the scanning parameters in taping mode. Another important phenomenon that we have to take into account is the mode switching in taping mode AFM. Well, actually, there are a lot of theoretical approaches to model the interaction of the cantilever and the sample. All these approaches gives us the energy curve, the curve of the dependence of the energy of interaction of the cantilever and the sample of approximately this shape as shown in blue color in this picture. The cantilever that oscillates in the taping mode represents actually the harmonic oscillator with some kind of parabolic energy curve. And depending on the set point and amplitude of the free cantilever oscillations, the result curve of this system might have different shapes. And it is possible to have the situation where this potential energy curve actually has two minimum or two minimum, and so the stable interaction between sample and cantilever is possible both within attractive and repulsive regimes. And the mode switching between two curves are clearly visible usually on the magnitude versus z curves that can be measured in any AFM. And here is the set of these curves, dependence of amplitude of cantilever oscillations on the distance with different amplitudes of cantilever oscillations. And if the amplitude of cantilever oscillation is large enough, the mode switching happens quite close to the beginning of the interaction of the cantilever with the sample. And the smaller the amplitude, this switch becomes in other point of the curve. And finally, when we work with the small amplitude in the order of 10 or 20 nanometers, we can avoid the mode hopping and always operate within the let's say the attractive regime. This switch between these two modes is clearly visible on the phase images, on the phase curves. So the dependence of the phase of the cantilever oscillations on the distance between cantilever and the sample clearly shows if we operate within the attractive or repulsive regimes. So this effect also should be taken into account when adjusting the parameters of operation in taping mode. So in general, we need to avoid the mode switching because it causes different artifacts and result in AFM images. The AFM can be the first attempt is to model the AFM and then to analyze with the linear theory is quite interesting, but in our experience was not useful enough. But there are simple equations that can be written here, and they're just based on the fact that the error signal that feedback system works with is the difference between the set point and magnitude, the value that is proportional to the amplitude of the cantilever oscillations. And the integral feedback works in this way, and the signal that we recognize then as the topography of the sample is proportional to the output signal of the feedback. So this set of equations gives us to two simple equations that shows us that the real topography of the sample, and these two equations are quite obvious, but the real topography of the sample is actually equal to the topography of the sample plus some error, and the error that we work with operating in taping mode is actually proportional to the derivative of the topography, to the velocity, to the speed of scan, to the velocity of the cantilever that the cantilever moves with, and to some time constant that is inversely proportional in its term to the feedback gain coefficient. So, taking into account all these quite general assumptions, we have some general as well ways how to optimize the feedback gain actually, and how to optimize other parameters in taping mode IFM. Well, first of all, the general term that we need to minimize error signal. We need to avoid mode hopping or mode switching in AFM. And we need to avoid max signal saturation that refers to the parachuting effects we've been talking about. So the integral feedback gain optimization might be done in the following way. Actually, the error signal is can be approximated with those kind of equation, even some parts of the second order can be taken into account, but in general, this equation is quite obvious as well, because when we have the large values of the feedback gain, the errors becomes high, and when we have the low values of the feedback gain, the feedback system just cannot, just do not work properly, and we have large error signal as well. We have to avoid mode switching, so we need to set the amplitude so that there is no other switching, and it can be controlled using phase signal. The phase signal is very sensitive to the switching of the mode of cantilever oscillations. And we have to avoid saturation of the magnitude signal. If it happens, we have to decrease set point, and if the set point is less than 50% of free amplitude, for the simple equation that we got on in the previous slide shows us that we need to adjust the speed of scanning just to decrease the velocity. And using all this quite basic and simple stuff, we are able to develop the algorithm that allows to automatically or literally in one click adjust the whole set of the scanning parameters in taping mode IFM that even quite difficult samples like self-assembled DNA origami in these examples can be scanned from the literally first attempt. This video shows how it happens. So initially, the several initial scan lines of the scan are used to adjust these parameters, and then the whole scan is completed, and we get quite nice result and high resolution image of the DNA origami. The scan in this example, the scan size is 300 by 300 nanometers. The same approach can be used to scan the variety of samples. For example, the fluoralkane F14H20 on silicon that has been shown already, and in this slide we also the phase contrast on this sample is shown. This sample is quite difficult to measure, and one can see that these results are quite high quality, and all scaling parameters are adjusted automatically here by pressing one button. Another example is the high-density polyethylene. Once again, the topography is shown in the left part of the slide, and in the right part of the slide there is a phase contrast. The scan size is 2 by 2 microns here. Both the topography and phase are clearly visible, and as far as one can see, do not have any artifacts here. Another example is the polystyrene blended with polymethyl metaacrylate. Once again, topography is in the left part of the slide, and the phase contrast is in the right part of the slide. Scan size is just 1 by 1 micron. Both the topography and phase contrast are clearly visible here. One more example is the copolymerized polystyrene with polyvinyl denfluoride. The topography here is again in the left part of the slide, and the phase contrast in the right part of the slide. As one can see, the lamellar structure uh, of the areas of the darker areas in the phase contrast are very clearly visible here. The parameters, once again, for phase contrast and for topography imaging are automatically adjusted by clicking one button using the basic principles that have just been described. And in the next slide, there is a closer view to the same sample. 600 by 600 nanometer slides are clearly show um, some details of this structure. And the another example is thermoplastic vulcanizate. Once again, the topography is in the left part, and in the right part there is a phase contrast. So the scan size in this example is 1.5 by 1.5 microns. So as far as we can see, the general approaches and the algorithm that have been developed by us to automatically adjust the tapering mode parameters allows to scan the variety of samples, and some examples have been given already, but the variety of sample is in the same time is the problem here, because the sample can have the very rough topography, or in contrast can be almost atomically flat. The sample can be quite soft or can be quite hard. So this whole variety makes this whole variety of the samples that can be or should be able to be measured by atomic force microscope are actually create the next problem of setting initial parameters for any algorithm that would allow them to automatically develop the parameters. First of all, because if we are initially far away from the optimal parameters and we start to scan 1, 2, 3 lines of the scan, then using some algorithm to adjust the scanning parameters, it takes some time. And the second and key problem here is then the cantilever can be broken. If your initial parameters are set it up so that you're going to scan the atomically flat surface, and then you um, um, start to adjust the parameters, automatically adjust the parameters for the very rough surface with roughness of half, or for example, 1 micron, the possibility that the cantilever will be broken is quite high. And this is the issue here, and this issue has to be solved. For this purpose, we decided to use the machine learning algorithms. In the beginning of each experiment, the user is asked to set up some parameters: the value of topography, roughness, stiffness, thickness, and charge of the sample. And after the experiment, the user uh, can save the measured sample features: its roughness, stiffness, thickness, or was it charged or not. This data is then upon the customer decision can be used for a machine learning that is based on the backpropagation method and uses the Broyden-Fletcher-Goldfarb-Shannon algorithm, quite simple neural network that has an input parameters: the resonant frequency of the cantilever stiffness, Q factor of the cantilever, and actually the scan size that you are going to have. Some initial parameters of the sample that, let's say, are verbally known, like thickness, charge, roughness, and stiffness of the sample, and all these parameters works as an input for the machine learning algorithm. And at the output of this neural network, we have the initial values of the uh, proportional and integral feedback gains, set point, and scan rate. And then the algorithm that is based on the linear optimization theory starts to operate with these initial systems. And this allows to actually save the probe along with to save the probe and to minimize the time required to adjust the optimal parameters. And in this video, there is another example. This is an membrane that is quite difficult sample as well to measure. We start the scanning process, then automated adjustment is done. It is worth to mention that this kind of sample has very rough surface. It contains deep pores, and these pores are dangerous to the tip. Because the scanner that is used in NT-MDT spectrum instruments AFMs has quite good performance. We are able to use a so-called safe probe feature. This probe automatically decreases the scan speed when the magnitude signal changes too much. And then automatically decreases the velocity of scanning when amplitude signal doesn't change too much when you go to the not so rough area. And this example shows that during the automated scan, we have a quite good quality of the results, and within them, and then after the manual attempt of the adjustment unfortunately allows to break the cantilever, and then coming back to the automated parameters allows to get the image with the almost good results, but the cantilever was already slightly damaged. Another example that is in the current slide is the aluminum oxide that is often considered as a greater sample for tips. In the left part of the site, there is an AFM image that were obtained using scantronic algorithm and the safe probe feature when the when the scan speed is automatically adjusted. And in the right side of the picture, there is the result of the manual attempt to adjust scanning parameters. For this kind of samples, the use of those kind of algorithms like scantronic is especially important and especially useful because it is possible to adjust the optimal scanning parameters in the manual way here. But while you adjust these parameters, the cantilever will be already damaged and you will not be able to get the proper results. So the scantronic is a technology that actually simplifies the adjustment, much simplifies and automate the adjustment of optimal scanning parameters in the most common mode of AFM, making, as we hope, the AFM technology much more interesting and much more widely spread in the community. Next point of today's talk is the rapid scan technology. Rapid or so-called fast scan is the topic in AFM community that is widely discussed for at least last 10 years or even more years. And there are two commonly used terms. First term is the high-speed AFM that is usually referred to the video rate AFM working with a scan speed of 10 till 100 frames per second or even with a higher speed. And this FM has its own niche, but they have small sample sizes usually. They allow topography imaging only, usually. These kind of instruments are very complex to operate with, and they have small field of view. Another group of so-called fast scan AFM is usually referred to the smaller field of view compared to regular AFM, and the scan rates that are about 10 times larger than the typical scan rates in AFM, and that corresponds to about to the order of 10 lines per second. Well, the key in this presentation we will talk about the fast scan option, and for this option the key limiting factor is actually the mechanical resonance of the scanner. We have been lucky enough to have a chance to check the well-known formula from the school physics school book about the dependence of the resonant frequency of the spring loaded with some mass, and these formulas works perfect, especially for scalar resonant frequencies in both xy and z direction. And the resonant in xy direction is usually the limiting factor that pushes developers to decrease the field of view and scan rate in xy direction, but to get the higher scan rates. We propose the Rapid Scan 100 technology, and this is the combination of mechanical design and digital electronic solutions that allows to speed up atomic force microscope by an order of magnitude approximately, but keeping the same field of view in xy direction, keeping 90 microns in plane scanning range. So the idea here is to damp digitally scanning resonance in X and Y using a combination of low pass filter and high pass filter and band pass filter, and as the result in this picture it is clearly visible that the resonant characteristic of the scanner becomes much less resonancy. And then keeping the same scanning range of 90 by 90 microns, it is possible to scan not just the atomically flat surfaces, but also the rough surfaces like a collagen surface in this example, with a scan speed of about 10 lines per second. And there is, by the way, 1000 points in each line, because usually when demonstrating the fast scanning in some AFMs, usually the manufacturers decrease the amount of lines, the amount of points in lines in X direction and the amount of lines in Y direction. Here there is 1000 by 1000, so there are 1000 by 1000 lines in each direction. And as far as we can see, this is the forward and backward lines are shown in the cross section. They're quite correlative. We can see that we're able to do this kind of scan even on very rough samples. Another example that is quite typical but quite difficult for both automatic adjustment and for the fast scanning is the calibration grating. The calibration grating is a standard, let's say, test signal, like a step signal for any adjustment system. And in this example, it is shown that we can automatically and rapidly scan this kind of sample with the speed of 10 Hertz, having at the same time 1000 points in each line and having 1000 lines along the Y direction. So this is basically it, and we are moving to summary. So the ScanT technology allows to eliminate common AFM artifacts, and it drastically improves quality of AFM results. The second important point that ScanT is significantly lowering cantilever consumption in any AFM lab. And together with ScanT, the rapid scan technology allows to increase the scan rates, typical scan rates, up to 10 times without compromising with maximum XY visible areas. The live shows of, I would like to thank a lot my colleagues, and first of all, Dr. Yuri Bobrov, Pavel Wiener, Andrei Gruzdev, and Dr. Stanislav Liesmint for their job and for their efforts to develop these new technologies. And I would like to invite everybody for live shows that will be available in the spring in Boston, Massachusetts, Phoenix, Arizona, and Orlando, Florida, in different exhibitions. And I would like to thank you for your attention, and your questions are very welcome.
Thank you, Vyacheslav. Very interesting lecture. And we got a couple of questions here. We still have some time, so don't hesitate to put your question to the questions window, which can be found on your GoToWebinar panel. So one of the the first and question which came from several participants is of course what is the possibility to get this software feature working on their systems?
Thank you, Stanislav, and thank you for this question. Yes, this feature is now available in NT-MDT Spectrum Instruments products in our AFM that operates with the PX family controllers. These are so-called PX, or sometimes it is called in the community P9 controllers. This feature is available. This controlling is available for those customers, and once these customers are interested in, they are very welcome to contact us, and these Scantronic options we will be happy to coordinate, and then to upgrade your system with the to remotely upgrade your system with it.
Okay, so the next question is following. Could you please summarize quickly the necessary steps to avoid parachuting effect?
Thanks for this question again. So there are several essential steps to avoid the parachuting effects. To avoid the parachuting, the most essential step to avoid parachuting effect is to avoid the saturation of magnitude signal. If we have the parachuting, it means that we have the saturation of the mag signal. If it happens, well, that means that the feedback system is not able to to work to react to the change in the topography. So if saturation happens, the good way would be to decrease the set point. If the set point becomes too low, so that it is less, for example, that 50% of the free cantilever of the amplitude of the free cantilever oscillations, or if it is low enough so that the sample might be damaged, because once you decrease the set point, you increase the force action between the cantilever and the sample. We need to adjust the scan speed, so to decrease the scan speed. And in the very general terms, to avoid the parachuting effect, well, theoretically, we have to increase the feedback gain, but increasing the feedback gain, we increase the noises up to the generation of the feedback loop. So we cannot increase it to the infinity. To increase the feedback gain as high as possible once the noises are acceptable, and to decrease the velocity. And then to decrease the velocity, because if once we scan slower, the feedback system has more time to react to the changes. And even this question is important, and parachuting effects are very very often one can see parachuting effects and parachuting artifacts in the images, in the AFM images published in the very reputable journals even, because even to avoid this quite simple and quite um, quite visible effect, we have to adjust several parameters: the feedback gain, the velocity, and the set point. At least 3 parameters has to be adjusted to avoid this effect. Well, this is basically it.
Uh, okay, the next question is how will we understand that tip has been damaged? Can we get it from resonance frequency, or maybe you can tell this from the image you get?
There are different cases. If the tip is hardly damaged, or if you have some particle, for example, that is parasitically attached to the tip, of course, one can see the change in the resonant frequency and resonant curve of the cantilever will happen. but most commonly it is visible from the picture, because once you're adjusting the scanning parameters and still are not able to get the proper result, or you have the for example, double shaped, all particles in the scan are double shaped, or some other artifacts that do not correspond to the well, to the general expected results. Um, this is the point where we have to stop and think if the cantilever is damaged or not.
Okay, the next question. So, what are the limitations when scanning liquid conditions and when the scanning is done above the room temperature? Does the Scantronic help with these issues?
Thank you for this question. The application of the taping mode in liquid is very interesting and a very important field. Well, first of all, the main point here is that the Q factor of the cantilever in liquid becomes much lower. As the result, the resonant frequency becomes much lower, and sometimes we have to say that we operate in liquid with the taping mode AFM with a Q factor of the order of 10. That sounds for liquid applications not too bad, but sometimes you might hear that we operate in liquid with the in taping mode with a Q factor of let's say 1 or 2. But actually the operation with a Q factor of 1 or 2 is not the resonant operation. This is not the taping mode anymore. This is some kind of other mode of IFM. This is just a general note about the operation in liquid. So there are limitations in liquid, and the algorithm that are used for automated adjustment of scanning parameters in liquid. At the same time, algorithm that used to adjust the scanning parameters in liquid in basic physical principles are the same. The physical principle that refers uh, to the parachute in effect, for example, or feedback loop operation. But at the same time, the resonant curve of the cantilever becomes quite complex in liquid. And once the resonant peak is properly selected and the uh, resonance and the oscillations, initial free oscillations of the cantilever in liquid are properly adjusted, then the same algorithm might be used to operate in liquid.
Okay. There are a couple of questions, and I will summarize them under single question. Is it possible to use Scantronic not only for tapping mode or resonance oscillatory amplitude modulated mode, or to some other modes?
Thank you. This is a very good question. Um, and there are two answers for this question. Well, first of all, the Scantronic is very useful for any taping mode based complex IFM mode, like scanning Kelvin microscopy or scanning capacitance microscopy, because even if you set up the parameters of taping mode for this and then are going to use the second pass modes or more complex mode that includes several lock-ins or much more signals to measure, the proper adjustment of initial taping parameters is well is important. It's not just important. It is the start point. If you do not adjust scanning parameters properly in regular taping mode, you will not get then proper results in Kelvin mode, AFM, or in capacitance microscopy. This is the first part of the answer to this question. So it is useful because if you for example damage the tip adjusting the parameters, and Scantronic allows you not to damage the tip, you then are not able to move forward with the more complex technique. And the second part is that we are constantly developing our technologies, and the Scantronic technology will be in the nearest future developed to the complex IFM modes, to the double pass IFM modes like scanning, capacitance microscopy, like magnetic force microscopy, like Kelvin microscopy.
Okay, we got actually a couple of more questions, but I think we'll answer all of them like in offline regime. Once again, I would like to thank all of you for attending the webinar, and thanks Vyacheslav for this nice talk. And this year we are planning to run a series of webinars. The next one is planned for March. This will be related to a combination of AFM with different optical techniques, and you're kind of welcome to join this webinar as well. So follow us, and we'll inform you about the new events like offline and online. So thanks you once again, and I think for today our webinar is finished. So see you next time. Bye bye.